Hello, 8th graders, and welcome to the Explainer. We're absolutely thrilled you're here. Today, we are setting out on a really fantastic geometric journey. Our title today is Formal Constructions and the Foundations of Proof. Now, if you've ever found yourself wondering how mathematicians know something is 100% true without just, guessing or squinting at a piece of paper, well, you are in the exact right place. Today, our main goal is to understand true geometric logic and discover how we can build unshakable mathematical arguments right from the ground up.
Okay, let's dive right into this. Here's a quick look at our roadmap. First, we'll untangle the difference between sketches and constructions. Next, we'll model the perpendicular bisector. Then, we'll connect those steps to formal proof. After that, we'll tackle a misconception that trips up a lot of students, do a quick check of your understanding, and finally wrap up with a recap and a transfer prompt. Let's go!
Section 1. Sketches versus constructions.
Now, what's really interesting about this is the stark contrast between these two methods. A measurement-based sketch totally relies on your eye, a ruler, or protractor to support your physical intuition. It's kind of like a rough draft. But a formal geometric construction, that literally throws the ruler's measurements right out the window. It relies entirely on pure logic, using only a compass to draw circles or arcs and an unmarked straightedge to draw lines. So remember, a sketch supports your intuition, while a construction supports a formal mathematical proof.
Moving right along to Section 2, Modeling the Perpendicular Bisector.
Let's actually get hands-on here. Imagine you have a line segment on your paper. We'll call the endpoints point A and point B, giving us segment AB. Step 1, you take your compass, place the sharp point firmly on point A, and draw a wide arc above and below the segment. Step 2, and listen, this is absolutely critical. You keep the exact same compass width, place the sharp point on point B, and draw a second arc. Step 3, look at where those two sweeping arcs cross each other and mark those intersecting points as C and D. Finally, step 4. Take your unmarked straightedge and draw a straight line connecting C and D. Boom! You have just constructed a perpendicular bisector.
Section 3. Connecting steps to proof.
So why do we do it this way? Well, Mathematical Practice 3 clearly states that mathematically proficient students must construct viable arguments and critique the reasoning of others. That means we don't just blindly follow steps, we make conjectures and build a logical progression of statements. We actually have to justify our mathematical conclusions. The steps we just took with our compass aren't just pretty art, they are the literal, physical building blocks of a logical argument. Let's see how this all builds together. Every physical step of that compass ties strictly to a foundational geometric reason. Think about it. When we drew those arcs from A and B keeping the exact same width, our claim was that the arcs have equal radii. The mathematical reason for that? The very definition of a circle. Then, when we mark the intersection C and D, we can officially claim that points C and D are equidistant from A and B. Why? Because radii of the same circle are strictly equal. See? We didn't need to invent any complicated theorem names. We just relied on the pure definition of a circle's radius.
Section 4. Misconception. Looks can deceive.
Let me speak directly to you for a second, because this trips up so many people. Eyeballing is not geometry. A massive misconception is assuming a line is perfectly straight or perfectly cut in half just because it looks that way to your eye. Another one is believing a ruler measurement is perfectly accurate. It's just not. Rulers have thickness, our pencils have thickness, and let's face it, our hands shake. Thinking an eyeball drawing or a ruler measurement counts as a geometric proof will steer your logic totally off course.
So the crucial point we want you to take away is this. A sketch supports your intuition. And hey, that's great for brainstorming. But only a formal construction based strictly on geometric definitions and executed with a compass and straightedge supports a mathematical proof. Unassailable logic, not our physical eyesight, builds the actual foundation of proof.
All right, Section 5. Check your understanding.
Let's test your logic with self-check number 1. Here it is. Does measuring a line segment with a ruler to find its exact center count as a formal geometric construction? I'll give you just a second to think about it and lock in your answer. And the answer is no way! Rulers create measurement-based sketches. Remember, measuring tools always introduce human error. Formal constructions strictly use a compass and an unmarked straightedge. That ensures the center is found through pure, undeniable logic, not a potentially inaccurate physical measurement. Awesome. Let's try self-check number 2. This one tests the reasoning behind the tools in your hand. Why must you keep the exact same compass width when drawing the arcs from point A and point B?
Really think about what the compass is actually doing there.
And this brilliantly illustrates the whole point. Keeping the compass width exactly the same ensures the intersecting points C and D are perfectly equidistant from A and B. It all comes back to the definition of a circle's congruent radii. A simple tool like a compass literally locks in the geometric definition of a circle to prove our lengths are perfectly equal. Pretty cool, right?
Finally, Section 6. Recap and transfer prompt. Let's quickly recap these core takeaways. First, sketches use measurement, but constructions use pure logic. Second, the compass and the straightedge aren't just for drawing, they are literal tools of proof. Third, every single construction step you take requires a specific geometric claim and a mathematical reason. And finally, by justifying those steps, that is exactly how you build a viable geometric argument.
To leave you thinking like true mathematicians today, here is a transfer prompt to chew on. We bisected a line segment today, but how might you apply this exact same compass logic, using equal radii, to construct the bisector of an angle instead? Imagine an angle on your page. Where would you place your compass point first to guarantee those equal distances? I want you to take that thought, grab some scratch paper, and experiment. Thank you so much for joining us for this explainer today, and keep constructing those brilliant arguments.